Welcome to the Electronics 101 presentation. I am Altbier, and I'll be walking you through this basic knowledge of electronics, including some theory and an outline of all the different components that are commonly used. This presentation is available at altbier.us/electronics. So let's start with a basic question. What is electricity? Electricity is a form of energy resulting from the existence of charged particles, electrons and protons. Electrons and protons have equal and opposite electric charges, with electrons having the negative charge and protons having the positive. And a good thing to note here is that opposite charged particles are attracted to each other. Now, protons are relatively static. They don't move around. Electrons tend to move from one object to another. So electrons can move through certain type of materials easier than others. Those easy materials to move through are called conductors or maybe semiconductors. And then some materials completely block the movement of electrons. Those are insulators. Resistance is the measure of the ability of electrons to move through a material. So the harder it is for an electron to move through it, the more resistance that material has. And the attractive force between positive and negative charges is an electromotive force, and that is called voltage. So negative electrons move towards positive voltage by way of a conductor. This flow of electrons is referred to as electric current. There are two types of current. You have alternating current and direct current. In alternating current, the direction that the electricity flows through the circuit is constantly reversing direction. The frequency rate of the reversal of direction is measured in hertz. That is the number of reversals per second. So when people say that the US power supply for AC is 60 hertz, what they're really saying is that it's reversing that flow of electricity 120 times per second. In direct current, in DC, electricity flows in only one direction, between power and ground. So between positive and negative, or power and ground. This arrangement has a positive source of voltage, which is something above zero, and ground, which is 0 voltage. And that's generally what's used in most modern day electric devices. Anything that has computational ability will use DC power. And the reason for that is the use of specific voltage levels can be used to indicate binary or logic states. So you might be asking, well, I plug my laptop or my PC into the wall power, which I know is AC power. How is that it's using DC? You might notice that the device that you're plugging into the wall, especially if it's a laptop, it's going to have a small brick attached to it and then a smaller cable that plugs into your laptop. That brick is a transformer that's converting the AC power into DC power, so that the flow of electricity going into your laptop is DC. And that's true for most electronic devices. Some of them can take the AC source directly, and then that transformer is internal to the device, so you don't see it as obviously as you do with a laptop power cord. Let's talk about conductors, semiconductors, and insulators. So materials that permit flow of electrons freely are called conductors. Examples of this are gold, silver, copper, etc. Materials that completely block the flow of electrons are called insulators. So rubber, glass, Teflon, etc. Materials whose conductivity falls in between a conductor and an insulator are called semiconductors. Semiconductors are part-time conductors whose conductivity can usually be controlled. And an electrode is a solid conductor that carries electric current. An example of this would be the lead wires coming off of a component that you're going to solder onto something. Those are electrodes, and it's because the lead wires themselves freely conduct electricity. Let's talk about silicon semiconductors. Many electronic components contain semiconductors, and silicon is the most common material used to build semiconductor devices. So silicon is spun and grown into a crystalline structure in wafers that will make up electronic devices. And then materials like phosphorus and boron can be added to the silicon to change its conductivity. So N-type silicon is created when phosphorus is added to silicon, and the resulting mixture is called N-type silicon because it has a negative charge carrier in the silicon. And P-type silicon is created when we add boron to the silicon. The resulting mixture is called P-type because it has a positive charge carrier. Silicon, one or both types of silicon can be used in semiconductors. An example would be a diode. A diode usually uses both the N and the P-type silicon in what's called a PN junction. Let's talk about the different units of measure and names for things with electricity. So current is usually referred to with the letter I, and its unit of measure is the ampere or amp. And current is the quantity of electrons that are going to pass over a given point. So voltage, which will have the symbol either V or E, is the electrical pressure or force. And it's sometimes referred to as potential. And this unit is the volt. Resistance, which is referred to by the letter R, it is referring to the amount of resistance that current flow is being resisted by. Because conductors aren't perfect, and semiconductors don't provide a full conductivity, there is an amount of resistance, and that resistance is measured in a unit called the ohm. Capacitance, referenced by the letter C, is the ability of a system to store an electric charge, and that unit of measure for capacitance is called the farad. Now with capacitance, the electrons are stored electrically in the device, and that's going to differ from inductance. So inductance, which is referred to by the letter L, is the tendency of a conductor to oppose a change in current flow through it. And inductors, they use magnetics to store electrons. So it's a little different than capacitors, but it's a little bit the same in that they're both storing electricity, and we'll get into that in a minute. The unit of inductance is called the Henry. Power is the work performed by an electric current. The unit of power is called the watt. Frequency, with the letter F as its reference, is the rate at which alternating current reverses the flow in a circuit. And the unit of frequency is called the hertz. And then load is what we call the part of a circuit which performs work. Either a motor or a light bulb, like an LED, etc. Those are loads on the circuit. All right, next we're going to talk about Ohm's law. So Ohm's law details a relationship among current, voltage, resistance, and power. This allows us to calculate a value giving any two of the other values. So some of the basic formulas are E equals I times R, This would be voltage is equal to current times resistance. The next one, I equals E divided by R. That's current is equal to voltage divided by resistance. And then R equals E slash I, or E divided by I. This is resistance is equal to voltage divided by current. Now these first three are what's commonly known as Ohm's law. The fourth element comes in. It's a power calculation that has been able to be combined with Ohm's law to bring us all four values and the inner relationships between them. So power would be equal to voltage times current. Now the chart on the right shows how we can use those four basic formulas to extrapolate a number of other formulas that would allow us to take any two values and calculate a third value. So for example, if I wanted to know what power was, and I had any of the two other values, I could use that one of the formulas here. So we have the P equals E times I is the original formula for power. But we can also, if we don't know what voltage is, we can figure power based on using current and resistance by doing I squared times R. Or if we don't know what current is, we can use voltage and, I'm sorry, not voltage, voltage and resistance. So voltage and resistance, or we can use current and resistance, or we can use voltage and current. But any of the two will give us the third. And so these formulas go around the wheel here, and there are formulas to figure out any one of these things giving any two of the others. Now, you might think, why do I need to know this? Well, let me give you a simple example. Say you're trying to wire up a simple circuit with an LED. You know the amount of current that the LED can withstand without blowing up. It's in the white paper. It tells you clearly it won't do well over this current. And you know how much voltage that your battery is going to supply when you plug it into the circuit. Well, you can use Ohm's law to determine the amount of resistance that you need to prevent your LED from blowing up. So you'll know whether you need a 50 ohm resistor or a 100 ohm resistor or whatever the resistor value is that you need. And that will keep your circuit going, but prevent the LED from being damaged. And I use blowing up as a term that can actually happen with some of the older LEDs. I haven't seen it happen much with a modern built LED. They tend to just burn up and turn black on you. So this can be a very important thing to know, how to at least calculate simple values like that when you're building a circuit. And let's talk about circuits. So electrons will not flow through an open circuit, which is depicted on the left diagram, but they're going to flow freely through a closed circuit, which is depicted in the right diagram. A switch is a device that allows for a circuit to be toggled between open and closed states. So if we look at these examples and imagine a light switch in your house, right? When the light is turned off, that switch is turned off, it's producing an open circuit, which is preventing the electricity from reaching the light bulb and going through the light bulb, because the electrons are not going to flow through this open circuit. But when you flip the light switch on, it closes this circuit, and now we have a nice closed circuit where the power source, whether it's a battery or in the case of your house, your home power feed, that power can now actually flow through the light bulb. So the electrons will flow around that circuit because it's closed. So that's how switches work and how circuits behave in open and closed states. Let's talk about parallel versus series circuits. So circuits can be wired up with components in a variety of ways that will either be in the form of a series circuit or a parallel circuit. And the difference is whether the components are in line or not. So in a series circuit, where the components are placed in line, the current is going to flow through each of the components the same, right? It's one single current flow around this circuit. The voltage across that circuit is going to be the sum of the voltages, the voltage drops across each component. So each component, as it uses the electricity, it may drop voltage along that path. So in our example where we have a battery, let's say it's 1.5 volts of power, and the electrons are going to go from the negative state to the positive state, right? So we're going to have electrons going to this first light bulb that, let's say this light bulb is going to drop half a volt. So he's getting 1.5 volts of power, of electricity, and when the circuit continues onto the next light bulb, that next light bulb is only going to get 1 volt of power because the first light bulb dropped a half a volt. And that could be a good thing and something you're planning for in a circuit, or it could be detrimental to your circuit. In this example, the second light bulb is going to be a little bit dimmer than the first light bulb because it's getting less voltage going through it. Now in our next example, a parallel circuit, the voltage across each of the components is going to be the same. And then the total current draw is going to be the sum of the currents of both of these. So it's almost like we have two separate circuits, but they're interconnected. So the current draw will be the combination of the current being used by both circuits. But the voltage is the same. So with our 1.5 volt battery example, the 1.5 volts is going to be applied to both of our light bulbs. And then the current will be the sum of what each light bulb is using. And that can be something that becomes a consideration as you're building circuits, whether you need to plug things in a series circuit or in a parallel circuit, because there are pros and cons for each and there are uses for each. So we talked about switches a second ago with open and closed circuits. There's actually several different switch types. So we're going to talk about the mechanical type differences between switches, where we have a toggle switch. That would be kind of like the light switch in your house. If you think of that, that's a toggle switch. It's going to flip on, it's going to flip off. You can have a slide switch, which is just on a slider that can go on or off or between different positions. You can have a dip switch like you see on some electronic devices like computers, where you can move the dips up and down. So it's similar to a slide switch, but it's more difficult to move, and that's on purpose because you don't want dip switches to be able to easily change their state. You want to force it to be moved if it's going to be changed. And then you have a tactile switch, which is also known as a momentary switch, which is more commonly known as a button. And that button will change state only when it's pressed, moving it back to its original state when it's released. So between the three mechanical types, toggle and slide switches easily move and remain where they're at once they're moved. The dip switch is more difficult to move, and tactile or momentary switches are easy to change state, but they move back to their original state once you're done pressing them. Now let's talk about the different electrical types of switches. So we have this SPST that stands for single pole, single throw, and it can also have a nomenclature of normally open or normally closed, and that refers to its initial state. Now an SPST type switch, it can be of any of these mechanical types. This is the electrical view of it. And the diagram off to the right here, this is our schematic symbol for that type of a switch. In its normally open state, it would look like this, and that just means its initial state is an open circuit, and then you would have to toggle the switch or slide the switch or push the button to get it to be a closed circuit. And then the SPST-NC, it's normally in a closed circuit state, so that toggle or slide or push button would make it move to an open state. Then we have single pole dual throw switches, and this is what this would look like. Imagine if you have a switch that switches between two different sources. So let's say I have, I'm going to use an old example. I have a TV splitter that's going to let me either flip a switch to make my PlayStation work, or if I flip the other switch, it lets the cable TV signal work. This is that type of switch. It's on. It's not like an on-off switch. It's not producing an open circuit on a single circuit. Instead, it's wired into two different circuits, and it will be on in this direction or on in that direction. So that's where single pole dual throw switches will toggle between those two states to make a decision, use this or use that. Then we have a dual position single throw, or a dual pole single throw switch, DPST, and this looks like that. It's almost like if you had two different circuits that had a common switch, and we're using a single switch to flip it on and off, but have it produce the same result in both circuits. That's what this does. So imagine if I have a light switch in my house that controls both a light and a fan, and they're on different circuits, but I don't want to have two different switches, one to control a light, one to control a fan. I can have a DPST switch where I throw one switch on or off, and it turns both the light and the fan on and off. That's one example. And then we have dual pole dual throw switches. So this is similar to the single pole dual throw, but it's doubled again. So imagine if I have four different devices that I'm choosing between paths on, and I have two different switches to control it. So that's the different switch types and their schematic symbols. Next, let's talk about resistors. So a resistor is a passive device that has two terminals or two electrodes coming off of it, that it's going to implement resistance on a circuit. So it's made up of a semiconductor that will implement a certain measured amount of resistance on the circuit. So you can use resistors to reduce the current flow. At the same time, they may act to lower voltage within circuits, depending upon how they're used. And the amount of resistance, as we talked about earlier, is measured in the ohms. Resistance are what's called a non-polar component, meaning it can be placed in either direction. Doesn't matter which direction you place it, it's going to work the same way. The resistance value is usually printed on the component in the form of colored stripes. Some resistors have 4 and some have 5, but the color code works for both of them, as you can see in the chart here. And then down below here we have the electronic symbol, the schematic symbol for a resistor. There's two different types that you can use. One looks like a jagged line, and the other looks like just a rectangle on the line. So photoresistors. Photoresistors are also known as light-dependent resistors, or LDRs. They're a passive component that work very much like a regular resistor, but they decrease the amount of resistance with respect to receiving light. So basically it's looking for light and luminosity and it will affect the amount of resistance it provides on the circuit based on the amount of light. So under dark conditions, the resistance of an LDR is going to be very high, like in the millions of ohms of resistance. Under bright conditions, the resistance is going to be lowered. It may be as low as 1 to 200 ohms of resistance. Now, photoresistors, just like regular resistors, are nonpolar components that can be placed in either direction in a circuit. And they're used in light-sensitive detector circuits or light-activated circuits. Like if you want to turn a light on or off based on the ambient light of a room, you would use a photoresistor for that. The photoresistor has two different symbol types, just like the regular resistor. It might have the jagged line or the rectangle, but it will have two arrows pointing into it, and this is an indication in the schematics that it's a light receiving device. Diodes and light emitting diodes, which a light emitting diode or an LED is one type of a diode. Not all diodes emit light. A diode is a two-terminal or two-electrode component that conducts electricity primarily in one direction. That means it has a low, ideally zero resistance to current in one direction, and a high, ideally infinite resistance to current in the other direction. This directionality indicates that diodes are polar components, meaning that they must be placed in a circuit in the proper direction. A diode's two electrodes are called anode and cathode. The anode is the positively charged electrode, and the cathode is the negatively charged electrode. So when placing them in a circuit, you would want the anode to be placed where the positive flow is, and the cathode where the negative or towards ground flow is. So a light emitting diode is a type of diode that emits light when activated. When a suitable voltage is applied to it, electrons that pass through the device will release energy in the form of photons. This effect is called electroluminescence, and the color of light will correspond to the energy of the photons released. So this can be adjusted when building diodes. So light-emitting diodes can transmit certain frequencies of light or nanometers of light that will determine what colors. Now, some of the cheaper diodes are set up just to show white light, and then they use the plastic housing around the LED to make it look like a certain light color. But there are many LEDs that have clear housings, and they will be tuned to sending certain light frequencies out that will be displayed as certain colors. The symbol for a diode is a triangle pointed at a line, and then a light emitting diode will have two arrows coming off of it to indicate the light coming off of it. But the symbol will look similar for a regular diode that doesn't emit light. It just won't have those arrows coming off of it. Capacitors. A capacitor is a passive two-terminal electric component that stores electrons in an electric field. The simplest capacitor is just two conductors separated by an insulating material that's called a dielectric. The effect of a capacitor is known as capacitance, which is measured in farads. Capacitors come in both polar and nonpolar forms. For example, a disc capacitor, a ceramic disc capacitor, is usually nonpolar, and you can place it in the circuit in either direction, where an aluminum electrolytic capacitor is going to be polarized, and you'll need to place it in a specific direction in the circuit, identifying the anode and cathode the same way you would with a diode to make sure it's going into the circuit in the proper way. So the cathode side of a capacitor is charged with electrons. These electrons in the charged capacitor will slowly leak through the dielectric until both the conductor plates have an equal charge. The capacitor is then discharged. So a capacitor opposes changes in voltage. So it can have a smoothing effect on a circuit by filtering out voltage spikes. So that is going to differ from the next component that we'll talk about, an inductor. But the main point of a capacitor is that it works in changes in voltage. That's a big difference, and it's because it's storing electrons in an electric field. It works different than other components as well. The symbols for capacitors are either two lines together with a separation that is supposed to show in the schematic the dielectric. This would be a non-polar capacitor, like a ceramic disc capacitor. Or then we have a capacitor with a line and then a curved line with that separation. And it usually will have a plus symbol on it somewhere to indicate which side of it is the anode side. And this is for a polarized capacitor. And then the symbol for a capacitor with two lines and then an arrow going through it, this is for a variable capacitor. This is a capacitor that can have variable charges. So next we're going to talk about inductors. An inductor has a lot of different names. It's also called a coil, a choke, or a reactor. It's a passive two-terminal electric component that stores electrons in a magnetic field. So similar to the way a capacitor stores electrons in an electric field, inductors store them in a magnetic field. So an inductor typically consists of an insulated wire wound into a coil around a core. And then the current that flows through the inductor around that coil, it will produce a magnetic field that is proportional to the amount of current flowing through it. Unlike a capacitor, which opposes a change in voltage, an inductor will oppose a change in current level. Inductors are nonpolar in that they will work in either direction in a circuit. However, because they're working with magnetic fields, the current flow will change the magnetic poles present around the inductor. So given that reversing those connections can lead to an opposite effect, some people use the term bipolar component to refer to a component like this that can have an opposite effect when it's reversed, but it will work in both directions. An inductor is characterized by inductance, which is the ratio of the voltage to the rate of change of current, and the unit of inductance is the Henry. Inductors are widely used in electric components, particularly in radio equipment. They're often used to block AC signals, allowing only DC current to pass. They're also used in filters that can separate different electronic signals into different frequencies on AC circuits. So they have a lot of uses in electronics. Their symbol is a bunch of half circles put together to try to imitate the look of a coil, which is what the inductor is physically. Transistors. A transistor is a semiconductor device that's used to either amplify or switch an electric signal or electrical power. It's composed of semiconductor material, usually with at least 3 terminals for connection to a circuit. A voltage or current applied to a pair of the transistor's terminals will control the current that is sent through another pair of terminals. So there are several different types of transistors, too many to list here. Each type has a specific layout and requirements based on what you're needing in the circuit. So you would use different resistors to produce different effects in your circuit. Transistors are non-polar in that they work in different layouts, but they will work with different results. So putting a resistor in a different direction in your circuit will produce a different result. Given that reversing connections can lead to opposite effects, this is called a bipolar component. Since the output of a resistor can be higher than the input, a transistor can be called an amplifier. It can also be called a switch, in that we can take a small amount of current in one place on the transistor and use it to turn on a big current in another part of the transistor. So in that way, it can be used as a switch or an amplifier or both. And transistors are used in a whole plethora of devices. They're included in almost every electronic device that's made. An integrated circuit, also known as an IC or a chip or a microchip, is a set of electronic circuits that are pre-built on a small flat piece or chip of semiconductor material, normally silicon. The integration of large numbers of tiny transistors into small chips results in circuits that are orders of magnitude smaller, faster, and less expensive than those that were built with discrete electric components. ICs are now used in virtually every electronic equipment, and they've revolutionized electronics. ICs tie these internal circuit paths into external electrodes via pins or pads, allowing for their integration into other circuit designs. So since ICs come in many shapes and sizes, with different internal circuit layouts based on what they're designed to do, it's very important to read the IC documentation for the IC that you're working with. This will ensure that you're properly connecting it into your circuit using the right pins to do the right thing. And that brings us to the end of our presentation. I hope you found this deck helpful and you learned something about electronics. While I attempted to cover the basics of electronics here, there's a lot more to learn. This deck did not cover everything. If you would like to know more, there's lots of resources online. There's lots of books on the topic. I'm a big fan of the Make series of books. They have a Make Electronics books. They have a Make Encyclopedia of Electronic Components book that are great. I also love the No Starch Press books. They have great ones related to electronics, like A Beginner's Guide to Circuits or 10 LED Projects for Geeks. I've used both of those books, and they're great. So yeah, if you want to learn more, there's lots of resources out there to learn more about electronics. I hope you enjoyed this presentation. Thank you.